In this video, we're going to be talking about projection onto a line and how it can be viewed as projection via matrix multiplication. But before we explain that, let's review what we know about projection onto a line. So if we are taking a vector B and projecting it onto a line that's determined by some vector A, so the line is the span of A, then that projection vector can be calculated essentially using Euclidean geometry. But what the formula boils down to is that the projection vector P is going to be a scalar multiple of A. And how that scalar is determined is by the inner product of A and B divided by the inner product of A with itself. This comes out of the geometric fact that the error vector E is perpendicular to P, and we can use that to solve for P. If you're in a crunch, you can just memorize this formula if you need to calculate the projection of a vector onto a line. Now, the purpose of this video is to point out that this projection can be accomplished via matrix multiplication. There's going to be a matrix that we also call P, capital P, such that if we take P times the vector B, we get the new vector, little p, the projection. So what is this matrix, big P? Our formula up here tells us that the little vector P is A transpose B over A transpose A times A. Now, I've decided to use transpose here to denote inner product, but really this is a dot product. This is another way of writing A dot B and A dot A. And I'm going to rewrite this expression a little bit. What I want to do is move the A over here. I can scalar multiply a vector on the left or right. It doesn't matter. So this is the same thing as having A, the vector, and then A transpose B, and then all over A transpose A. But now what if I group these terms differently? In particular, I'm going to group A and A transpose together, and then I'm going to keep A transpose A on the bottom. And then I'll have a vector B. This is all equivalent to P, but now since I've collected terms together, I can, instead of having an inner product in the numerator, I have an outer product. This term, A transpose, is now the outer product of A with itself. What that means is that instead of producing a scalar, it's going to produce a matrix. And so this formula is of the form matrix over A transpose A, so it's being divided by a scalar, so times a scalar, times the vector B. And it's this matrix times scalar that forms the projection matrix P. So I'll write this here as PB, where P is now 1 over A transpose A, that's a scalar, times the new matrix A transpose. Now I'm going to be doing an explicit example in just a moment, but before we get around to doing that example, some brief remarks are in order. The first remark that I want to make is that this matrix P that we're producing has the property that if you square it, you get itself. Conceptually, this should make sense. If you take a vector B and you send it into some line or some vector space to produce the vector P, which is the image of PB. If you apply P again to PB, now you're applying P to P, and since it already lives on the line A, it really shouldn't change anything. This concept is that P squared ought to be equal to P. The second remark is that you can project to the right or you can project down. What we've been doing thus far is downward projection. We take a vector P and we project it straight down. Well, what if we had projected rightward instead? We could have taken this vector B and projected it this way, onto the line determined by E. Well, E is the rightward projection of B, and it is also in and of itself a projection. What makes that formal is the following kind of set of equations. If you take the identity matrix and you take the difference of the identity matrix and P, this projection matrix we're describing, then just by formal nonsense, this tells you that the identity times B minus PB is B minus P, and that's E. And also, I minus P has that same property where if you square it, it works out to be I minus P. So both P and I minus P are projection matrices. And what a projection matrix really is a matrix that has this property. If P squared is equal to P, that's the defining property of being a projection matrix. Later on, particularly when we talk about the least squared problem, we're going to be looking at the projection of B, not just onto a line, but into an arbitrary vector subspace. And it will be really handy for us to think about projection matrices when we handle that problem. Rather than do a completely new example, I want to revisit an example that we did before. In the video that precedes this one, we calculated the projection of B onto A in the specific case where B was the vector 1, 2, and A was the vector 3, 1. So we had the blue line determined by A, and we projected B down to get the green vector P, and we worked it out using the formula, and we saw what that ought to be. The green vector was 3/2, 1/2, and the error vector, which we also calculated, was this. So when we calculated this before, we used the projection formula A dot B over A dot A. To get a scalar, that's this part right here, and then we multiply it times the vector A. That's this part right here. But now I want to work this same example in a new way. Instead of having the scalar come from the dot product, which is an inner product, I want to use the outer product, A transpose. We're going to move the vector A over here, and that means that A transpose is now going to be a matrix. This is the matrix that we call P. The A transpose is A dot A. That's still going to be a scalar, so this is 1 over that number, A dot A. We're going to scalar multiply the matrix P with that. And then B is hanging out here on the right, and B is still going to be here. So all of this is going to become the matrix P. We multiply it times the vector B, and that's also going to give us the same answer for the projection vector that we get from projecting B onto A. So when we're all said and done, we should still have 3/2, 1/2 as our final answer. So calculating this, we have P is 1 over A transpose A, and then A transpose. So 1 over A transpose A is 1 over A dot A. That's 3/1 dotted with 3/1, which is going to give us a 1 over 9 plus 1, so that's 10 here. This is how we get this scalar. Now A transpose is maybe the tricky part. Instead of taking a dot product, we're taking an outer product. So rather than having row dot column, it's column dot row. So we're now going to have a 2 by 2 matrix result from this calculation. That's going to be this matrix 9, 3, 3, 1. That comes from the column 3, 1, matrix multiplied times the row 3, 1. And all of this assembles together to give us the matrix P. Now we're going to take that matrix P and multiply it times the vector B. Now if you like, you can scalar multiply through the 1/10 into this entire matrix if you just want to see a matrix, but I don't like dealing with fractions, so I'm going to leave my 1/10 as a scalar on the outside until I'm all done. So I take the matrix 9, 3, 3, 1 and multiply times the vector 1, 2, and that gives me the vector 15, 5, and then I'm going to move that 1/10 as a scalar inside to get my final answer of 3/2, 1/2, which is actually the same thing that I got here. For those of you who are following along with my written lecture notes, you can find one more example there that I'm going to leave out of the video. That's an example of an explicit calculation of a projection in an inner product space other than Rn. So in particular, the example involves some continuous functions in the inner product space made out of continuous functions. And calculating that inner product involves doing some integrals. So you can read the notes if you want to see more about that.